So in the last video, we considered the unsymmetrical diatomic molecule hydrogen fluoride and looked at the molecular orbital picture and predicted that the electrons, or more of the electrons, spend more time on fluorine than the electrons spend more time on hydrogen, thus leading to the observed dipole moment, which has a partial negative charge on fluorine and a partial positive on hydrogen. Let's consider the MO diagram for carbon monoxide, CO gas. Lewis structure you would draw for carbon monoxide would have a triple bond between carbon and oxygen. It would have a positive formal charge on the oxygen and a negative formal charge on the carbon. But we know that the actual charge distribution would have a partial positive on carbon and a partial negative on oxygen, because oxygen is the more electronegative element. So we know that the formal charge on the Lewis structure is not actually a good representation of real charge on carbon monoxide. Can we do a molecular orbital picture that would correctly predict that we have a partial positive on carbon? We can draw a resonance structure for carbon monoxide that looks like that. It has just a double bond between the carbon and oxygen. And if you were to draw this resonance structure, you might predict that a Lewis base would very much like to attack carbon, because carbon has an unfilled octet and is therefore electron deficient. And if you looked at this, you might very much predict that carbon would like to attack a Lewis acid because it has a negative formal charge. But we know it doesn't really have a negative charge, it really has a partial positive charge. So Lewis theory doesn't do a very good job. As it turns out, carbon monoxide reacts with Lewis bases at carbon and reacts with Lewis acids at carbon. So no matter who you are, you're talking to carbon when you react with carbon monoxide. It would be nice if we had an understanding of the bonding in carbon monoxide that would make that, that would explain that would make that make sense. So we start with carbon and the oxygen, and we know that the 2p energy level and the 2s energy level of carbon are fairly close together. And we also know that because of the larger nucleus, the orbital energy levels for oxygen should be lower in both cases, right? The 2s orbital and the 2p orbital. But they're going to be more distinctly low for the 2s, and that's because of that penetration, where the 2s atomic orbital has an inner lobe that spends some time very close to the nucleus, where the 2p doesn't. So the 2s orbital is going to be much more sensitive to the presence of more protons in the nucleus than is the 2p orbital energy level. So we probably don't have to worry about the 2s orbital and the 2p orbital on oxygen mixing with each other, but we will have to worry about both of them mixing with the 2s orbital on carbon, and we do have to worry about the 2s and the 2p orbital on carbon mixing with each other. So there will be sp mixing. Right? And like the case with the fluorine, with the interacting, both the 2px orbital and the 2s orbital on fluorine interacting with the hydrogen 1s orbital, we have this 2s orbital interact in the middle, right, in between the 2p and the 2s energy level on oxygen, which means it can interact with both of them at the same time. Because of sp mixing, we can predict that the overall orbital energy diagram will look like a fiddle. It will have sigma 1 G, pretty low, and it will have sigma 3G lower in energy, or higher in energy than I. So our overall shape will be the same as it would be for diatomic carbon or for diatomic nitrogen. And carbon monoxide is in fact isoelectronic with diatomic nitrogen. Because it has a total of 10 electrons, right? A triple bond and a lone pair on each atom. You'll notice that I've tried to draw this to scale so that pi y and pi z are the same amount below the 2p energy level for oxygen as pi star y and pi star z are above the 2p energy level for carbon. Because we know that the sum of the pi y and pi star y orbital energy has to be equal to py on oxygen plus py on carbon. And we know that the sum of pi z and pi z star has to be equal to the oxygen and the pz on carbon. So those should be symmetrically distributed. It should also be true that the sum of the 4 sigma orbitals, 1g, 2u star, 3g, and 4u star, should be the same as the sum of the 2s orbitals and the 2px orbitals. Notice I haven't put any electrons in anywhere. I can create the orbital energy diagram without considering electrons. Right? Eventually, I'm going to want to put 4 valence electrons on carbon and 6 valence electrons on oxygen and have a total of 10. And when I fill them, I'll fill sigma 1g first, then 2u, half filling the pi y and pi z before I completely fill them, and then sigma 3g will be filled. So there are 4 bonding electrons, and only 2 anti-bonding electrons. Sorry, 6 bonding electrons and only 2 anti-bonding electrons. We try 8 bonding electrons, sigma 1g, pi y and pi z, sigma 3g, so there are 4 sigma bonding electrons, but there are also 4 pi bonding electrons. 8 bonding electrons minus 2 anti-bonding electrons is 6 net. Divided by 2 is equal to a bond order of 3. So we correctly predicted a short, strong bond, as would be reflected in the Lewis structure that we normally draw for carbon monoxide with a triple bond. So the energy diagram looks very similar to what it would look like for diatomic nitrogen. But the shape of the orbitals does not. Because sigma 1g is much closer in energy to the 2s orbital on oxygen than it is to the 2s orbital on carbon, it's going to be significantly misshapen with a lot of electron density lying on the oxygen atom and much less electron density lying on the carbon atom. Sigma 1g will in fact be formed with a fairly small coefficient of the 2s orbital on carbon, plus a very large coefficient times the 2s orbital on oxygen. The oxygen 2s orbital making a much larger contribution than the carbon 2s orbital. That means there's a lot less of the oxygen 2s orbital left for the other orbitals. Right? Sigma 2u star we can form by either destructive overlap between the 2s orbital on carbon and the 2s orbital on oxygen, or constructive overlap from the 2p orbital on oxygen and the 2s orbital. So in essence, what we're going to have is we're going to have some coefficient times the 2s orbital on carbon minus some smaller coefficient times the 2s orbital on oxygen, but then also plus a decent sized contribution from sigma 2p on oxygen. So we're going to have a lot of this 2s orbital on carbon. We're going to have destructive interference with respect to the 2s orbital on oxygen and constructive interference with respect to the 2p. It's kind of hard to visualize that, but what you're going to have is a one-node orbital. Right? With a node in here somewhere, we're going to have a orbital looks like that, has a pretty large amount of electron density on the carbon, decent amount of electron density on the oxygen, and no in between the two. So it's going to be anti-bonding, but it's not going to be as strongly anti-bonding as an ordinary anti-bonding orbital would be in O2, for example. Right? It's going to be more similar to the diatomic carbon situation or diatomic nitrogen, where the bonding orbital is much more strongly bonding than the anti-bonding orbital is anti-bonding. Right? Sigma 3G is also going to take components from all three. There's not going to be much of that 2s orbital left anymore. But there's going to be a lot of this 2p orbital from the carbon. So sigma 3G is going to take pretty much none of the 2s orbital. It's going to take a little bit of the 2s orbital on oxygen, or sorry, 2s orbital on carbon. Yes. A little bit from the 2s orbital on carbon, but not much. A double prime. It's going to take almost nothing from the 2s orbital on oxygen, so we're just going to ignore that. It's going to take some of the 2p orbital on oxygen, but then it's also going to take a fairly large amount of the 2p orbital on carbon, right, which is the highest energy of those orbitals. There's going to be two nodes, because it's the next highest energy orbital. The nodes are going to be roughly through the center of the carbon and the center of the oxygen, because the 2p orbital on carbon has a node through carbon, and 2p orbital on oxygen has a node on oxygen. There's going to be a pretty large lobe out here, good size bonding. It's going to look like that, right? It leans heavily towards carbon. This one leans so heavily towards oxygen that all three of the other sigma orbitals are effectively going to lean towards carbon, right? This one leans way towards oxygen. Sigma 4U star now takes very little electron density from the 2s orbital on carbon because there's not much left. A triple prime times psi 2s carbon. And then it's going to have destructive overlap between the 2p orbital on carbon and the 2p orbital on oxygen. And the largest coefficient by far is going to be the 2p on carbon. Right? So we've got an extra node. There are going to be three nodes here. Because we've got destructive interference here and we've got destructive interference there. It's going to have the nodes through the nuclei, but it's also going to have another node here. As the energy of the orbital goes up, as the number of nodes in the orbital goes up, the energy goes up. So 0 nodes and then 3 nodes. And this one, of course, is empty. The other 3 sigma orbitals are filled. So that's what the sigma system looks like. The pi system is also going to be unsymmetrical because pi y is going to be formed from a large coefficient on the py orbital on the oxygen plus a smaller coefficient times the py orbital on carbon. So we've got a little bit of carbon orbital and a lot of oxygen orbital. And I'm exaggerating to some extent here. But what you're going to see is you're going to see a high symmetry orbital, but you're going to see a high symmetry orbital that leans towards oxygen. And then pi z is going to look the same, but rotated 90 degrees. And then when we do pi star y, oxygen destructively interferes with a pretty large coefficient from the 2y on carbon. So we've got a big carbon orbital, and we've got it destructively overlapping with a small oxygen orbital. So it's going to have that same cloverleaf shape that you would predict for diatomic oxygen, but it's going to have bigger clovers on carbon than it does on oxygen. It's going to have a new node. So this is pi y here, and this is pi star y here. So we know that pi y lies more on oxygen than it does on carbon. And we know that pi star y lies more on carbon than it does on oxygen. So if we put these orbitals here on the same diagram so we see everything in place, and then pi star z kind of looks the same, except that it's out of plane. And then pi y looks like this. And pi z looks like this. So our bond order is 3. Right? We predicted that we would have a triple bond. And if you look at the frontier orbitals, the position or the portion of the orbital energy diagram where you switch from having a filled orbital to an unfilled orbital is referred to as the frontier orbitals. And something that MO theory predicts or says is that the frontier orbitals are going to be the ones that are most useful for predicting reactivity. So if I blow this up, and my frontier orbital, sigma 3g, is below pi star y and pi star z. And sigma 3g is what we call the HOMO, the highest occupied molecular orbital. And pi orbitals are what we call the LUMO, stands for lowest unoccupied molecular orbital. And together, the HOMO and the LUMO, highest occupied molecular orbital and lowest unoccupied molecular orbital, are referred to as the frontier orbitals. If you are a Lewis acid, you're going to look for the highest energy electrons that the system has to give. So Lewis acids take electrons from the HOMO. Lewis bases put electrons into the LUMO. If you're looking to give electrons away, you're going to want to give those electrons away to the lowest energy orbital that's available to you. So if we want to know where Lewis acids will interact with the molecule, what we want to know is what does the HOMO look like? Where is the largest lobe on the HOMO? And that's sigma 3g. And sigma 3g has a larger lobe on carbon than it does on oxygen because it had contributions from both the 2s and the 2p orbital on carbon and only a contribution from the 2p orbital on oxygen, which meant that it had contributions much more from the carbon orbitals than it did from the oxygen orbitals. Sigma 1g predicts that the partial negative charge will be on oxygen, because the low energy electrons, right, the pi y and pi z and the sigma 1p, those low energy electrons spend a lot more time on oxygen than do on carbon. So the number of electrons spending more time on oxygen is larger than the number of electrons spending more time on carbon, leads to a partial negative charge on oxygen. But that's irrelevant, right? If you're the Lewis acid, you're not looking for where the highest electron density is at the low energy orbital. You're looking for where the highest electron density is in the HOMO, and that's on carbon. So Lewis acids are going to prefer to interact with carbon. And in fact, when carbon monoxide interacts with iron in your hemoglobin, it interacts strongly from this sigma 3G orbital on carbon and binds carbon to your iron. If you're a Lewis base, you want to put your electrons into the lowest energy orbital that's available to you, and that's the pi star orbital. But the pi star orbital has much more electron density on carbon, right? Bigger lobe on carbon. So you're going to tend to gravitate towards where the electrons, or where the orbital is. The orbital is on carbon. The pi orbital lies mostly towards oxygen, but those electrons aren't relevant for the reactivity. For the reactivity, what's relevant is both sigma 3G and pi star Ys and pi star Z have larger lobes on carbon than they do on oxygen. Lewis acids take the electrons from the sigma 3G orbital, the HOMO, and that's on carbon. And Lewis bases donate electrons into the pi star Y or pi star Z orbital, and that has the largest lobe on carbon. So everybody likes to react with carbon, and the molecular orbital picture will accurately predict that, unlike the Lewis picture. So there's asymmetry, right? The asymmetry of sigma 1G leads to the observed dipole moment, and the asymmetry of sigma 3G and pi star Y leads to the observed reactivity. Molecular orbital theory, although it's a pain in the ass, and you're probably completely confused by it, is a much better picture of the actual bonding in a molecule. Now, do you have to know it? No, not really, but I wanted to give you this series of videos. Thus far, though, we've only done 2 atoms at a time, just diatomics. Well, it's useless to an organic chemist if you can only do diatomics. So we need to be able to extend this into molecules that have more than 2 atoms. And I'll have a couple more videos on that, and then we'll go away from MO theory. It'll come back second semester.